I'm Anil Kumar, and in this video we will try to understand how to apply Rolle's theorem. The question here is, verify that the function f of x equals to sine x in closed interval 0 to 2 pi satisfies the three hypotheses of Rolle's theorem. Then find all numbers C that satisfies the conclusion of Rolle's theorem. Right. So let's explore this function f of x equals to sine x within the given interval. So let me sketch this and then we'll verify. So sine x is kind of like this within the interval 0 to 2 pi, where the maximum value is 1, the minimum is minus 1. So this is from plus 1 to minus 1. Now let us see how we can verify that it satisfies three hypotheses of Rolle's theorem. So we are considering the function f of x equals to sine x in the closed interval 0 to 2 pi, right? Now when I say closed interval 0 to 2 pi, in that case a is 0, b is equals to 2 pi. What is f of a? F of a is equals to sine 0, right? That is which is equals to 0. F of b is sine 2 pi. That is also equal to 0. So what we have seen here is that f of a is equals to f of b, and both are equal to 0. In the graph you can see these are these 2 points, right? So these are your points a and b, right? Rolle's theorem states that the three conditions are: 1, that the function f of x is continuous, right? That is first thing. As you can see, the sine function is continuous in its entire domain, and therefore it is also continuous in its closed interval 0 to 2 pi, right? Because a sinusoidal function, right? So that's the first condition which is satisfied. The second condition is that f of x is differentiable in open interval 0 to 2 pi. So we know f of x is equals to sine x. F dash x, the derivative, is cosine x. Now cosine x is continuous and f of sine x is differentiable in its entire domain, and therefore it is also differentiable within the given domain open interval 0 to 2 pi, right? Third condition is that f of a equals to f of b. The closed interval given to us is from 0 to 2 pi. What we have seen is that f of 0 equals to f of 2 pi, and the values is 0. So that means the three conditions for Rolle's theorem are satisfied. Now the second part of this is, then find all numbers C that satisfies the conclusion of the Rolle's theorem. Now what is the conclusion? Conclusion really is, then there is a number C in the open interval AB, which in this case is 0 to 2 pi, that f dash C is equal to 0 in open interval A to B. In our case, this interval is from 0 to 2 pi, right? So that is what we can conclude from the Rolle's theorem. So we have to find these C's now. Now we have found that the derivative is cosecant x, right? So basically, we can now equate cos x to 0 and find the solution in the open interval 0 to 2 pi, right? So we know that cos of x is 0 for x equals to, you can actually think like this. Cos of x is a function which is kind of like this, right? So it is 0 at pi by 2 and 3 pi by 2. Right? Or you could use special triangles, or you could use calculator, right? So cos of 0, that means x is equals to cos inverse of 0, and this gives us two values within this interval. One of them is pi by 2 and the other one is 3 pi by 2, right? So the value of c, so we can say c1 is pi by 2 and c2 is 3 pi by 2, right? So these are the two values where the derivative of this function is 0, right? So where f dash c is 0. So as you can see from here, these are those points, so which is pi by 2 and 3 pi by 2. So if I draw a tangent, we'll get a horizontal tangent at these points. So for this particular function sine x, in the closed interval 0 to 2 pi, it is continuous, it is differentiable within this open interval, and therefore, and the values at 0 and 2 pi are same, equal to 0, and therefore there is at least one point. In this case there are 2 points, c equals to pi by 2 and c equals to 3 pi by 2, where we have horizontal tangents, right? So those are the answers in our case. So this is the answer for us. I hope you understand how to apply Rolle's theorem and what really it is. I'm Anil Kumar. You can always share and subscribe my videos. Thank you and all the best.